you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
So now we've talked about probability of single things happening. Now we need to talk about multiple events. So these are when we're doing, say, one thing like rolling a die, but we're looking for or winning when there are different kinds of outcomes. Now these outcomes could be mutually exclusive, meaning the two outcomes cannot happen at the same time, or they could be non-exclusive, meaning that it's possible for two things to be true at the same time. For example, if we're rolling a single die, the probability are when we're looking at the number being even or the number being odd, those are mutually exclusive. A single number cannot be both even or odd. This situation is an example of not being mutually exclusive, because if we win if the number is either even or the number 2, well, 2 is an even number, so in those cases both of these things can happen at the same time. This would be another example of mutually exclusive. A number could not be 3 and also be even. Now the reason we need to think about this, the formulas for when we do probabilities are different depending on whether the events are exclusive or not. If we know that two events are mutually exclusive, if we want to know the probability of A or B happening, then we just add the probabilities. So on a die, getting a 1 or a 2 would be mutually exclusive, so to find the probability of getting either a 1 or a 2, we would just add the two probabilities together. Also, in this case, they're mutually exclusive, so we can just add the probabilities. There are situations when they are not mutually exclusive, in which case we need to factor in, because what it ends up when we're counting these cases, we're double counting this case. So if we count the number of 2's, there's 1, and count the number of evens, there's 3 even numbers, but we've counted the 2 twice, so we have to subtract that out. So there's only one case where you're both even and 2, so we had to subtract that out because it was being double counted. So ORs typically is, again, an addition problem. The only thing we have to be careful about is this mutually exclusive. So let's look at an example with the mutually exclusive. Now we're dealing with playing cards. Remember, in a deck there are 52 cards, and there are 4 suits. Remember, we have ace, king, queen, jack, and then 10 on down to 2's. And there are 2 colors, reds and blacks, and there are 4 suits. So in this case, probability of being red and or an ace is not mutually exclusive, because we could have a red ace. So the probability of red plus the probability of, that was supposed to be a P for probability here. So probability of red plus the probability of an ace. And now since they're not mutually exclusive, we have to get the probability of it being both. I don't know why I put that in parentheses there. I'm just really having trouble today. So the probability of essentially a red ace. So the probability of red, half the cards are red, so that's 26 out of 52. And the probability of an ace, there are 4 aces in the deck, so that's 4 out of 52. And there are 2 red aces in the deck, so we have to subtract that. So we get 28 out of 52, which we would then want to reduce. We could divide that by 4, so we get 7/13 as our probability as a fraction. Now, kings and queens, there's not a single card that's both a king or a queen, so these are mutually exclusive. So we just have to add the probability of a king plus the probability of getting a queen. So there's 4 of those, so 4 out of 52 and 4 out of 52. So we get 8 out of 52, or Divide that by 4, we get 2/13. So those are OR conditions. Again, we're adding the probabilities, but you have to consider whether they are mutually exclusive. Okay, our last topic here on probability is going to be AND events. So we're going to be doing, say, two things, selecting two objects, flipping two coins, etc., and we want to know the probability of a combination of the events. In this case, we need to, when we look at the formulas, decide whether the events are independent of each other, meaning can the outcome of the first event affect what happens on the second? If the two events are, if the first event cannot affect the outcome of the second event, they are called independent. And if the first event can affect what happens on the second, then they are called dependent. So if you're flipping 2 coins or 5 coins or 10 coins, those are independent because the flip on each coin does not affect another one. Rolling 2 dice, what happens on the first dice does not affect the second one. When we're selecting objects from, say, a bag or a jar, it depends on whether or not we are replacing the object after the first draw. If after each draw we look at it and decide did we get the outcome we're looking for and then put it back in, the events are independent. If we pull out multiple objects without replacing them, then they are called dependent events. So let's look at an example here. Well, first the formula. So if you know 2 events are independent, then the probability of both events happening, we multiply the 2 probabilities together. If you know that the 2 things are dependent, then we're still going to multiply the probabilities, but we don't multiply by the probability of just B, but we have to multiply by the probability of B knowing or given, that's what this symbol means, that A did happen. So the classic problems on these are selecting marbles from a bag. And how you know if they're independent or dependent depends on replacement. If we draw a marble from the bag, we look at it and decide success or failure, and then put the marble back, shake it up into the bag, and draw again, those are independent. So with replacement is independent. So the probability in this bag, so our bag has 10 marbles, 4 red, 5 blue, and 1 yellow. The probability of getting a red and a blue marble, so the probability of getting a red is 4/10. Now again, that red marble is put back into the bag and shaken up, so there's still 10 marbles in the bag and this mixture. So the probability of blue is 5/10. We multiply those probabilities, so we get 0.2. The probability of getting a red followed by a red would be 4/10 times 4/10. And the probability of yellow followed by yellow is 1/100th. Now it's possible to get 2 yellows because remember, we draw the first yellow, look at it, record it, and then put it back into the bag, so there's still a yellow one. Now let's look at what happens when we are not replacing. So let's look at the same set of events. So when we get the probability of a red followed by blue, we assume success. So on the probability of red, that was 4/10. Now for the second, we assume we're holding a red marble. So there are only 9 marbles in the bag, and now there are 3 red, 5 blue, and 1 yellow. So there's still 5 blue. So we get 5/9 on this part of here, the probability of blue given that it was red. Multiply those probabilities. So again, we get different probabilities, sometimes greater, sometimes less when we have the dependent events. Probability of a red followed by a red. Well, the first draw, there are 4 reds out of 10. Now we're holding one of the reds. So there's 9 marbles in the bag, and we're holding a red one, so there's only 3 red left. Again, we multiply those together. The probability of getting 2 yellows, you probably can understand, is going to be impossible because on our first draw, there's a 1 out of 10 chance, but now we assume success here, so we're holding a yellow marble. There's none left in the bag out of the 9 marbles, so we get 0/9. So we get 0/90 when we multiply, or a 0 probability. So good luck working the problems on the probability, and talk to you for the next unit, which will be on counting principles.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready?